Thank you, and thanks. So I won't show a few. I will show a few equations, but not as many as in the last talk. There's going to be more pictures, I promise, this time around. So the title here: Viscoelasticity of Planetary Interiors from Seismic to Convective Timescales. There's two parts today, and then Friday as well. So hopefully by the end of the second talk on Friday, it'll become a little clearer why I chose that title. So starting with images such as these, you have seen, I don't know whether Wedge showed exactly those kind of images, but we have shear velocity, so at 100 kilometers of depth, color-coded. Slow velocities are red, fast velocities are blue, and corresponding to this attenuation, and I'll talk a lot more about attenuation in the second talk, 1 over q. So these are, if you take the inverse, of course, of this, these are small q's, these are large q's, and the color coding corresponds to high attenuation here in red, corresponding to the low shear velocities here in red. You can see that the two correlate more or less, even though these are separate studies. The two correlate more or less. And in the end, what we want to know is, first off, how do we interpret these pictures? What's behind the change in velocity and the change in attenuation? And obviously, the two are related somehow. And then, moreover, once we have some state here in terms of temperature, composition, and so on, everything that we can think of in the upper mantle, what does this mean then for convection calculations? So how does this translate this temperature into a viscosity, for example? So that's what the talk will evolve around. And I'll start first, very basic. I think I have an outline. Yeah. So defects, very important, as you'll see. I'll try to convince you that defects are really key to understanding the upper mantle. And then I'll start with flow laws, so behind viscosities. And then on Friday, depending how far we get today, flow laws. And then I'll talk about more the seismic properties. So that the difference is these flow laws, that's steady state convective deformation. Transient creep, we'll see that determines seismic waves. So the properties of seismic waves and tidal deformation, for example. And then applications of some of those. So that's very, very broad where we're going. Of course, yeah?
Would it be a fair thing to say right away, in my mind, I'm starting to think of attenuation at the top of the mantle, and then I know that there's attenuation at the bottom of the mantle, and I don't know what defects do at the top or bottom of the mantle. Is it fair to think that what's happening at the top is happening at the bottom in your talk?
I'll try to address that a little bit. So when we get to the mechanisms that cause attenuation, I'll try to mention both parts of the mantle a little bit, as much as we know. We know a lot more, as usual, about the upper part of the mantle than we know about the lower part, but maybe there are some inferences that we can make. So I'll entertain the question again in the second part. So from the beautiful seismic images to what we think is really pretty here, a peridotite, xenolith peridotite. So this pale green here is mostly olivine. The important part in both, so this is a cross-polarized light image of a similar rock, maybe not quite as fresh as this one here. But you can see that, right, we have crystalline grains. That's one of the main themes, right? We can't just think about grain interiors, at least that's our view. You have to think about crystalline grains. The Earth is not a single crystal, and a lot of what we infer about the properties are based on this polycrystalline nature of the material. So pale green, the olivine. Then we have some brighter greens. It's a little difficult to see here, some brighter greens. So the olivine, clinopyroxene, then some spinels. And here in the cross-polarized image, we have also orthopyroxene. So these are the main constituents of the upper mantle. And yes, I'll take a little bit of a material science approach to all of this. Basically, we're reducing it to the most simple system. And as far as we've gotten experimentally in particular is just looking at olivine, polycrystalline olivine. So for the most part, I'll just simplify right here. And a lot what I talk about is this behavior of the olivine standing as representative for the whole of the rock. When we talk about crystals, then we have to look at crystal structure. And the reason for showing this simple structure here, cesium chloride, is that it turns out that a lot of the flow laws, for example, the constitutive relationships that were mentioned yesterday between stress and strain were derived from metals. So a lot of the background in material science has been done on metals. And they tend to be cubic. Most metals are cubic and therefore much simpler than the silicates. So that's something else to keep in mind, and I'll point that out again when I get to it. But here, the most basic crystal structure, 2 atomic species, they form an ordered structure. And you can expand this simple cubic, face-centered cubic. The difference is you have chlorine in both of them. The size of the second ion here is cesium or sodium, right? That determines, so the size and the bonding structure here, ionic bonding, determines how these atoms are ordered in the crystal structure. So I'm going over this relatively quickly as background, jumping to the silicates, which of course here, so olivine structure, as I said, very important. And you can see right away in comparison to these structures here that silicates tend to be much more complicated. That's a function of the bonding is different. We have covalent bonding rather than ionic bonding. And the other part is that we have a number of different atomic species that we have to accommodate, right? And that relates back to Bill's talk yesterday. The major elements in our solar system here are a few of them: magnesium, oxygen, and silicon. That's what forms the bulk of the upper mantle in terms of the olivine structure. But in terms of the mantle as a whole, that's the bulk of the mantle. So we have to make crystals that accommodate these major elements that are so much more abundant than everything else. Right? And therefore, we form these more complicated structures. And that's one of the big tensions between taking models from material science, where they were derived for metal with 1 atomic species, and applying them to something that looks like this, which is obviously the unit cell here, much more complicated. The building blocks, very briefly, you have this tetrahedrally coordinated silicon. You can see the tetrahedrons here, but the silicon is hidden inside. You can see that light blue dots here surrounded by the oxygens. And then the M sides, the metal sides, mostly magnesium, but we know that there's also some iron in here. So some of this is iron, some of this is magnesium. These are octahedrally coordinated. And then the sites, the octahedral sites are slightly different in the crystal structure. So you have yellow and then these orange sites here. But this is going into more detail than I'll use, just to point out the different colors in here. Metal in general just means iron or magnesium versus the silicon, right? And the different bonding environment. So metal as a very broad term. Well, in olivine, yes, you can make nickel olivine, for example. Then you'd have nickel sitting there. So, or calcium or anything else, So one of the things to keep in mind later on when I talk about defects and in particular dislocations is that the bonds in this environment, the covalent bonds, are not all equal. In particular, the silicon-oxygen bonds are the strongest bonds in the system. So when you try to deform later on the crystal, those are the ones that tend not to get broken. Right? So paying attention to where these tetrahedra sit tells you then what are your likely weaknesses in the crystal structure, as in you can imagine planes here where you don't cut any of these silica tetrahedra. In fact, so here's the orientation of the crystal. So the B-axis is shown here, the A-axis here, and we're looking down onto the C-axis. Or here, the different notation here, the 0, 1, 0 plane, that's perpendicular to the 0, 1, 0 axis. So the B planes will be through this. So perpendicular to the B-axis will be perpendicular, will be here. And you can see that that looks pretty open, at least in this representation here. We're not cutting any silicon-oxygen bonds. So this will be one of the planes of weaknesses in the olivine structure. So large spacing of these 0, 1, 0 planes. And then here's the A-axis, the 1, 0 axis. These are much more closely spaced. So that right here tells you something about the crystal, that it's anisotropic, right? Significantly anisotropic, and that will come up in a few places.
How do you decide which one is the 100 plane and which one is the 010? I mean, how do you define your reference frame? Is there a rule?
From essentially, you have to look at, so I didn't go into all the crystal systems. So in the end, it's a little bit of a convention, but then it relates to the symmetry properties of the crystal. So, and yeah, related crystal systems have related symmetries, and then that's how the axes get designated in the end. But I mean, ultimately, it's arbitrary. So you have to pay attention to your symmetry of your crystal, and then you designate certain directions, and those directions have certain properties. So, I mean, there's nothing.
I know. Why is it X direction in this direction rather than this?
Yeah, it's in the end, it's a convention. Yeah, there's nothing per se intrinsic, but just as with defining pressure, positive or negative, once you have a system, you have to stick with it within that system.
Is it an arbitrary convention, or is it like A is strongest or C is?
No, as we'll see, those vary then, and so depending at which property you look at, it's a little bit more complicated. There's not intrinsically a relationship between strongest and weakest, or fastest and slowest. I'll show a little bit of that.
Right. There are different settings you can also put those axes in, and so you can look up different symmetry tables, and so these directions can change depending on how you put your reference frame.
No, so for a particular crystal.
No, you can have like an O, you can have like an ABC in one direction, or you could change it to like.
No, typically.
The point is we've agreed on these reference frames.
Right.
We've been agreed on for 100 years.
Or more.
So they're set.
Right. So you don't change that anymore.
We don't change them. We define them. It's over.
Right.
There is no ambiguity. There is nothing.
No.
It's just the way it is.
Right. So, yeah, I'll show a few examples of properties, how the anisotropy is based on this, and you'll see that they don't necessarily correspond to. Okay.
No, I think we're going to carry on with the talk.
We can discuss that afterwards. So, so from the previous slide, so now I'm just rotating around B. So A is going to be flipped down actually, and you have a different view of this. Again, you see the tetrahedra here, the silicon inside of it, and what you can see here that in this looking down on A, you can see that the oxygens are nearly hexagonally arranged. So there you can recognize the hexagons here, they're a little bit distorted. Overall, the symmetry of the olivine is orthorhombic. So looking down on the 1, 0, 0 plane, you can see, I'll get back to a little bit to anisotropy, but not a whole lot. But in everything else that I'll talk about later on, of course, in the background is this, that you have this crystal structure. So when we talk about diffusion, when we talk about dislocations, when we talk about grain boundaries, any defect will, of course, be relative to this crystal structure. So that's something a little bit to keep in mind. So anisotropy due to crystal structure, that's something that we just mentioned. So the length of the unit cell, A is the smallest, B is the largest. So there's not a 1-to-1 correlation. C is intermediate. And then something interesting, again, I might come back to this, is the velocities. So, of course, the velocities are based on elastic moduli. I'll mention those in a few slides down the track here. But just as an example, again, the p-wave velocity, fastest along A, slowest along B, corresponding to this large spacing of the B planes, right? So if you think of this as a spring, I'll kind of refer to that. Of course, that's not exactly accurate, but that's a picture to keep in mind. If this is a spring, you're compressing it in this direction, right? The spring constant essentially is the smallest in the B direction, very loosely speaking. But you can see that for Vs, the relationship is a little bit different, and in fact, the maximum shear velocity does not correspond to any of the crystallographic axes. So it's more complicated than that. Right? So maybe that answers some of the questions. It's convention, but yeah, that convention goes back quite a ways, so we stick with that convention. So elastic behavior, I just hinted at thinking of these as springs. Of course, Hooke's law here, stress, some spring constant and strain, or force, spring constant and displacement. This is based on that these atoms in the crystal structure have unique equilibrium positions that derive essentially from a repulsive energy of the electron shells and then an attractive Coulomb potential. Right? And where those two balance, they have different dependencies on distance. So you can see that sketched here. And where the two they overlap, where they two have a minimum, this is where the equilibrium distance is of the different crystals here in the lattice. So the equilibrium distance is determined by this potential here. Right? And this equilibrium distance, this is your spring constant essentially. So if you push on this crystal, we're pushing against these potentials and trying to shorten it or trying to extend it. And this is where these elastic constants come from. But you can see that depending which direction you push on it, especially for olivine, you can see again that these elastic constants here are anisotropic. And Young's modulus, we don't use that really because we don't have very many tensile situations in the Earth. We mostly have compression here, the bulk modulus, and then in particular also the shear modulus. So shear modulus either G or mu. The letters change a little bit depending which field you're in or who is presenting something. And I'll come back to this again as well. The elastic moduli are of the order of tens of gigapascals. So that'll become important. So harmonic versus anharmonic behavior, in part I'm defining things that I'll be using and that you may have heard already in talks here. Harmonic behavior, you can see that at low temperatures, especially, so thermal energy causes vibrations around the equilibrium position. So we just established we have an equilibrium position, again outlined here by the different potentials. Thermal energy means that the ball here at the bottom of this bowl rolls around a little bit. And at low temperatures, you can see it's almost symmetric. So this is harmonic behavior. Of course, low temperatures for us in the Earth aren't that interesting. What we're more interested in is high temperatures. And then you can see that the potential becomes asymmetric. So when the ball starts rolling around here at the bottom, it'll go further in this direction, then it'll go in this direction, and you have essentially anharmonic behavior. But this changes also the average equilibrium distance. Here, this R naught is changed, which means that as the higher the temperature and the more asymmetric this rolling around becomes, the longer the bonds get. And this is something that just came up in the talk before. That's thermal expansion, right? That's the thermal expansion coefficient in the end. How much how much time does the atom really spend at longer distances away for a given temperature? Right? So that also goes back to very basic principles, looking at the potentials of these atoms. And then a little bit of thermodynamics. Again, background, internal energy. So the energy content of a system. Again, this was touched on in Alan's talk. So the energy content of a system, we have this interatomic bonding, right? That's the bonds that I talked about, silicon-oxygen bonds and so on. The kinetic energy, that's the temperature. That's the rolling around here. And that gives you an internal energy, total energy of the system. And again, in the Earth, so material science is mostly concerned with temperature, but in the Earth, pressure is very significant, and in planetary interiors, of course. So in addition to temperature changing or being able to change these potentials, we also have pressure. So we need to take pressure into account, so we have an enthalpy instead of just an internal energy. So pressure and temperature are lumped here together in this enthalpy, and so pressure and temperature, as you can see here, is very important for the state of this atom in a crystal. And then the next part, of course, that's the fun part. That's the entropy that again came up. And entropy is disorder. So all of this, what we had before, is sort of orderly, and now we go into disorder, and that turns out to be very important as well. This is, for example, configurational entropy. There's many more kinds of entropy here, but the entropy is maximum. So if you have two parts A and B, if you have an equal mix of the two, you have maximum disorder, and therefore the entropy is maximum. Right, so very brief definition of entropy, but we'll use that when we then think about deformation. So I'll jump around a little bit trying to motivate why we have to go back and think about deformation more fundamentally. Again, Hooke's law, right? And we want to apply Hooke's law to this glacier. You can see right, very nicely. You can see visually this ice is flowing. And ice is crystalline. Ice is basically a rock that flows, that has a viscosity. So it's a crystalline solid. So thinking about Hooke's law, okay? So ice turns out has a Young's modulus, and I just put the Young's modulus here because it's a nice round number, is 10 gigapascals, 10 to the 10 Pascal, right? So that's the spring constant. Then a strain epsilon here of 1, yeah, the strain is probably much larger than that. So 10% strain epsilon of 0.1, you take a cylinder, you shorten it by 10%, right? So obviously when you have ice or convection, your strains get very large. So you have E, you have this epsilon here. Now, can we separately estimate the stress? And the ice flows to first order due to gravity, so it's driven down the mountain by gravity. And then the pressure you get out of this is just density times G times the thickness or the drop of that ice. So very round numbers here. The density, roughly 1,000 kilograms, 10 meters per second, and say 1,000 meters. You end up with something like 10 to the 7 Pascal, right? The pressure here, or if you then think about the stress, that's 10 to the 7 Pascal. So comparing these two numbers, 10 to the 10, that's your spring constant. You're pushing it on it with 10 to the 7 Pascal. This ice shouldn't flow, right? If you just take the elastic moduli, this ice should be going nowhere because the force that you're pushing on it with is far too small relative to the spring constant. And it's even worse if you think about mantle convection simulations. So the elastic moduli of any rock-forming minerals are of the order of 100 GPa. Of course, there's a variation depending which mineral and which modulus you're talking about, but that's the order roughly, versus convective stresses are something like 0.1 megapascal, right? So you have many more orders of magnitude difference here. That's what you're pushing on the rock that has this kind of spring constant. So we shouldn't have any kind of convection. There should be no movement. Everything should be nice and elastic and orderly. Of course, this is where the fun begins for us, in that you have defects, right? Nothing is perfect, and I'll show thermodynamically why that is so, that nothing is perfect, that you always have defects. So we're going back to very simple crystals here, very simple sodium chloride here, the two species shown here, and we can define many different types of defects. That's just one example, a Frankel pair. Basically, you have two missing that are then interstitial somewhere else in the crystal lattice. So overall, when we have defects, we always have charge balancing. So we always have to balance the electrostatic charge. So hence, these kind of configurations where if you take one out in a Schottky pair here, you also have to take another one out. But so there are defects where you can see the regular order of the lattice is broken. Basically, you're something missing, something is sitting in between. And of course, semiconductors, right? That's how they work. They're doped with an impurity. But if you apply this to the Earth, so gallium arsenide here, an indium impurity, if you apply that to the Earth, right? We heard yesterday that we have, a few atomic species that make up the majority, and all these rare earth and everything else is an impurity that sits somewhere in the crystal structure and distorts it, basically. And that's behind, of course, partition coefficients. And if you look partition coefficients between different mineral species and mineral in the melt, is that you have to stuff something that is much larger, much smaller than the majority here in a crystal structure. Right? So defects, many different types of defects here, and I won't go into details of those. The question is, why do we have defects thermodynamically, right? So if you look at this, the point defect, if you want to make a point defect, it seems obvious that you have to use energy to do that. You have to distort the lattice, right? If you have a larger atom sitting in a site that's not designed for it, you're distorting the lattice surrounding it. And then you also have to satisfy bonding constraints, right? That's the covalent bonding. It's a directional bonding. The lattice that you stuff in a defect site might not be suited to the directional bonding that you're forcing it into. So certainly, when you have a defect, the enthalpy increases. But then, of course, you go to the entropy, right? And disorder is good, more entropy. So that's what in the end balances this increase in enthalpy, that for small defect concentrations, the increase in the entropy is greater than the penalty that you get by increasing the enthalpy. Right? So, and that's the minimum Gibbs free energy. So again, very schematically shown here. Here your enthalpy, and that's balanced by the entropy. You can see initially the entropy increases very steeply, so that the resultant, the sum of the two, the Gibbs free energy here, again has a minimum. Which means, so if you're plotting energy versus defect concentration, what I said earlier is that you don't have any perfect crystal, and the reason is that the energy state of a crystal is actually lower when it has defects. Right? So you reduce the total energy of the crystal by having a finite number of defects, and the reason is this entropy. And you can see that here, the minus sign. And the other thing you can see here is that this entropy, or the total sum here, is dependent on temperature. Right? That's a key point. The energy here and the number of defects, therefore, is dependent on the temperature. Right? Temperature-dependent defect concentration. So you can do that all thermodynamically. Yeah?
Well, is this true for all crystal structures or minerals, that there is some finite number of defects that leads to a minimum enthalpy?
Yeah. It's Boltzmann statistics, basically. So, you can play games, right? If you go to absolute zero, then, this is a different problem, right? So, but once you're at finite temperatures, that's always the case. That's pure thermodynamics. There's not much else to it, pretty much.
I mean, what percent, when you say a finite amount, how many, what percentage?
Yeah.
How much can that vary? Can it be a lot? I mean, or is it just a very small amount of defects?
So I'll just throw out ppm level, but in detail, right, it becomes very complicated because you have to calculate then the bonding environment, right? Then it depends on the crystal structure of the atomic species. You have to, in effect, measure all these enthalpies and entropies. And as we've seen, there are many different defect types, so it's a little bit more complicated. But sort of ppm level is, roughly what you have. And yeah, going back to this is Boltzmann statistics. It'll become important as I'll show later on. So, okay, do we have the answer? We have, so the perfect crystal wouldn't flow, right? You need defects in order to make anything happen here. But point defects, are point defects really the ones that we need to look at for the Earth? And for this, we have to go a little bit further. Now we discussed point defects. We have to go to line defects. And line defects, so here is a transmission electron microscope image. So before, I just showed cartoons of point defects. Right? And the size of a point defect, if you think about it, the size of an atom is of the order of angstrom, right? 10 to the minus 10 meters or so. So here, I'm actually able to show a real picture, albeit a transmission electron microscope image. Scale bar is here of what is a screw dislocation. I'll discuss what that is, a screw dislocation in an olivine crystal. So everything evolves around olivine. Screw dislocation in olivine. And now the key difference is before, for point defects, there were the atomic scale. We could use Boltzmann statistics. For these line defects, they're much more macroscopic, and therefore you can't use thermodynamics anymore. And that, I'll highlight that again, point defects are temperature sensitive. These line defects, these dislocations, are not controlled by temperature. That their generation is not controlled by temperature. And that's, the difference is the different scale. These are macroscopic objects, so basically quantum mechanics does not apply to that same degree. Yep? That essentially tells you something about the orientation of the dislocation line. So that's, dark field image. I can go into the details. That's, you basically shine it in the transmission electron microscope. You shine an electron beam through a very thin foil of a mineral, and then you can take the central beam that goes right through and remove it. And as the beam goes through the crystal, it gets diffracted by the lattice planes. These lattice planes that I showed earlier. And then you pick a particular diffraction spot, and that is what this tells you here. So it tells you the orientation of these lines here.
Are the wiggling ones also screw dislocations in other directions? Or?
No, I'll get to that. I'll say a little bit more about dislocation. So this is next. I'll talk about dislocation. So hopefully, I can't go into, all the details, but a little bit better feel for this. So point defects, line defects, and we'll look at line defects here. So lattice planes in a crystal, again, cubic is very simple. You can visualize things very nicely. So here you have your, and again, this is a metal, just one atomic species. You have your crystalline planes, easy to see here, just the planes. And if you insert a half plane, you get an edge dislocation, right? You can see that. So here's the half plane, and the line that terminates that half plane goes in and out of the screen here, basically, right? From a slightly oblique view, but it continues in and out of the screen. So you insert an extra half plane, and that is called dislocation. And in particular, this is called an edge dislocation. So we can characterize this, and material scientists have spent a lot of time characterizing dislocations. Basically, you can describe a dislocation by a Burger's circuit. So here's your dislocation line, here's your extra half plane, and you travel around the dislocation, and because you have this extra half plane, there's an extra step up here relative to down here, and that extra step here is the Burger's vector. That's your characteristic for the dislocation, this Burger's vector, this extra step that you have to take where you have the extra half plane. And again, this is an edge dislocation going in and out of the crystal here, and you'll notice the Burger's vector is a vector. It's perpendicular to this dislocation line, right? It has an orientation, and that orientation, hence the whole discussion about crystallographic directions, of course, has a direction in the crystal lattice, right? It's specific to this particular crystal lattice.
Sorry. So is there significance to where you drew the Burger's vector? Can it be one?
No, where the Burger's vector is not significant.
Only the direction.
Yeah, that the Burger's vector, the direction and the magnitude, but the location, this is kind of arbitrarily drawn, right? So the key part for the edge dislocation is that it's perpendicular to the dislocation line. And I already mentioned screw dislocations. Oops. Yeah, okay. Actually, here, again, imaging this. This is a very high resolution, again, transmission electron microscope lattice fringe image. You can see actually lattice planes in the TM image. And you can see here that you can imagine, it's a little bit hard to see, but right here, you have an extra half plane, right? So we can, again, directly image this in these very high resolution images. And you have to look very closely. You can see an extra half plane in the bottom part as well, right? So these are real. These are not constructs, these dislocations. You can actually directly see them if you have high enough resolution and a suitable material, of course. So screw dislocation, the same concept. You have a dislocation line. You, again, have a Burger's circuit, but you can see now here's the Burger's vector, right? The Burger's vector in this case is parallel to the dislocation line. That's the difference between screw and edge dislocation, and you can see that the offset here is different. And I'll show that in a few more cartoons. So it turns out, to Ved's question, you always have screw and edge dislocation. That's part of the same dislocation, right? In the end, to offset to cause strain in a crystal, you always have screw and edge dislocations together. And so strain due to dislocation creep, you can, this is the standard cartoon. If you have a grandma with a very heavy piece of furniture on a carpet, instead of pulling the carpet all at once, you just put this little fold in the carpet, and then you advance the fold, and you just lift up individual legs to move the carpet along, right? The concept, and this is where the concept of a defect comes in, instead of having a solid crystal and needing to break all the bonds at the same time, the way the dislocation moves is that you just break, so this extra half plane here, right, you just break individual bonds. You don't have to break the whole crystal all at once. But as you can see, as it moves through the crystal, you produce strain, right? So that's the key advancement of a dislocation, is that it's much easier to produce strain. You don't have the resistance of the whole elastic modulus of the crystal anymore. And similar for edge dislocation, again, shear is shown here. The edge dislocation moves through, and I'll show that. So this little, movie here, you can see here's the edge, and here's a screw dislocation going through the crystal and producing strain. Right? I'll show that again. So the edge dislocation here, screw dislocation here, the same dislocation line, moving through the crystal and producing strain, breaking always only locally bonds rather than having to break the entire plane all at once. So that's the great feature of these dislocations, in that they make it easier to deform a crystal. And what we see in the TEM, those bright lines, is in fact the strain field or stress field, depending how you look at it. Right? The lattice is distorted. Here's your edge dislocation. The lattice is distorted around the dislocation and therefore produces that strain field. And that's what you see macroscopically. And here's in shear, of course, the screw dislocation. So a little bit further along, crystallographic planes, right, going back to the pictures of the olivine crystal structure that I showed at the beginning, these dislocations move preferentially on certain glide planes in the crystal structure, right? Certain planes where it's easier to break bonds. These are glide planes or slip planes. And again, going back to atomic potentials a little bit, here's your potential. The dislocation line sits in these valleys. And then going a little bit further, but that's how far I go with dislocations. There's much more to it, but just to give you a feel for it, the dislocation advances from one of these valleys into the next one, actually not by the whole line moving all at once, but by these kinks in the line advancing through these valleys. So the important part is that with these dislocations, you have a mechanism where you just locally have to break bonds, and you can produce strain macroscopically with it. Right? That's why that glacier was able to flow. That's why we have convection in the Earth, because we have mechanisms such as this that make it much easier to deform crystals. And so the important part is that we have glide planes that are involved in this. So that's the crystallography, the crystal symmetry, the crystal structure comes into this. So we make dislocations not with temperature, but by, for example, what's called Frank-Reed sources. You have a dislocation line that is pinned, and then you apply a stress. That's the key part here, and that's an elastic line, and you just bow it out. And the more stress you apply and the longer you apply it, the dislocation becomes larger and larger, right? It slips, as we just saw through the crystal structure, and eventually it curls around, and you have the stipple part is the slip part. Then you're ready to make the next dislocation. So as long as you apply the stress and you have these two pinning points, you just keep bowing out and making more and more dislocations. So the key part is, in contrast to point defects, what makes dislocation is stress. So that's the convective stress that multiplies these dislocations. And again, you can image these obstacles to dislocation motions. I just mentioned, pinning points. Here we can see that these dislocations, so you have more than one dislocation in a complicated crystal like olivine, different planes, different glide planes that you can imagine through the crystal structure, and they interact, they get hung up on each other essentially, and I'll get to the next topic here. They start to form coherent structures. And these coherent structures, where these mesh very nicely here, we call subgrain boundaries. Right? You can see what are called free dislocations here in the interior, and you can start to see these tangled dislocations forming subgrain boundaries. So that's not the full story. We get back to diffusion here, actually, in that an edge dislocation can move up in its plane, right? So you have this extra half plane, and you can imagine that that the half plane, essentially the whole half plane, can climb, and this happens by diffusion. So if you have tangled dislocations that are hung up on each other, they can get around each other by diffusion, by climbing climbing up one of the glide planes. And the key difference between edge and screw dislocations is that screw dislocations don't have this extra half plane, so they can't climb. So only edge dislocations climb. This becomes important, I'll only touch on that, if you look at models for dislocation creep. Right? Models of dislocation creep come back to this concept that you have climb of dislocations, of edge dislocations.
Is diffusion random without any direction preference, or diffuse from high pressure to low pressure?
So it's a little bit more complicated, right? So each dislocation has its own stress field surrounding it, right? Yes. As I showed a little while ago. So because the lattice here is squeezed together, the lattice here is squeezed together, and here's extension. So the external stress field interacts with the internal stress field of the dislocation, and so the whole diffusion process is a little bit more complicated, taking those different stress fields into account. Right. So just to summarize, you have temperature doesn't really affect dislocations in the sense that it doesn't produce dislocations, but dislocations can be annealed by temperature. And the mobility of dislocations, how fast they can move, is also controlled by temperature. Right? So directly not produced by, in contrast to point defects, which we saw earlier, the number of point defects is temperature dependent. And then shear stress, this is what generates dislocations. So they're sensitive to shear stress and interact with an applied shear stress, whereas point defects, and again, that's a little bit variable, but generally don't interact with the shear stress. They're mostly temperature sensitive. So just as a rough guide, how to view dislocations versus point defects. So carrying on with that, going from dislocations to grain boundaries, as you saw in the TEM images, right? Here you have dislocations, spaced throughout. Overall, you can see that the lattice of the whole crystal has a curvature because we have these extra half planes in here. Right? So the crystal bends just by the fact that you have dislocations in it. And if you now collect all these dislocations, you can start to make subgrain boundaries. Right? This network of dislocations that I showed earlier, you can imagine that these form subgrain boundaries that separate coherent pieces of the crystal. So here, this is all one orientation. That's a different orientation, and there's a subgrain boundary in between. That's shown a little bit more schematically here, and you can define an angle that defines. So here's that Burgers vector again in here that I mentioned earlier, right? That's the Burgers vector, essentially the lattice spacing, and then this h is the dislocation spacing. And you can see that if you have a lot of closely spaced dislocation, then the angle becomes this angle here in the end becomes larger. So you can make a lot of subgrain boundaries, a lot of dislocations. Extra half planes in here, you have a larger tilt boundary. So you can again see that's macroscopic. If you look at a different mineral here, quartz rather than just olivine, I thought I'd put something different in. You can see these subgrain boundaries, right? What you see in cross-polarized light under those extinction is these are subgrain boundaries. So these regions of similar grayscale have similar orientations, so they correspond to these kind of patches, and then where the grayscale changes, you have an array of dislocations in the crystal. Yeah?
Why do the defects tend to concentrate together?
So again, there's a question of energetics, and then also, as I said, the dislocations become entangled. So the dislocations that I showed earlier in the TEM image were in fact in different crystallographic planes. Right? And you can imagine these are lines, and the lines crossing each other. And in order to get past each other, that's when I mentioned climb. Right? They have to climb. They have to somehow get around. They feel each other. The stress field, in particular, of the dislocation feels each other. And that contributes to them getting stuck and forming these subgrain boundaries. The other part of it is, again, energetics. It's having a dislocation line. If you think about energetics in the interior of a crystal, right? You have an energy penalty because you distort the crystal lattice. If you concentrate all these distortions into one area, the subgrain boundary, you reduce the overall energy state of the crystal. So that's why temperature anneals these dislocations. They're able to migrate into these subgrain boundaries, for example. So in material science, right, this is where, again, we have to become a little bit careful. In the material science world for metals, you can actually see that you can construct grain boundaries from arrays of dislocations. You just have many closely spaced dislocations, and you can, instead of a subgrain boundary, you now form a grain boundary by having an array of dislocations. Here are the lattice planes, and here the array of dislocations. Right? So that brings on the subject of grain boundaries. And the question is, why do we want to look at grain boundaries? Grain boundaries are present in every rock. So any kind of rock that you pick up from the crust or the mantle, crystalline rock, will be a polycrystal, won't be a single crystal, and therefore has grain boundaries in it. So the key point is that as a crystalline defect, right, a defect relative to a perfect interior of a crystalline grain, of a crystal, they are defect and they have very distinct properties, and I'll show a few of them. So grain boundaries as such affect diffusion, therefore also deformation, seismic properties, I'll show that on Friday, electrical conductivity, anything that you measure for polycrystalline rock is affected by the presence of these grain boundaries. So we need to know something about these grain boundaries if we want to know something about the behavior of the rock as a whole. And again, a grain boundary given by the misorientation of the two sides, so different lattice planes here, and the characterization of this is the misorientation. Yep?
So is there a particular significance to the difference between subgrain boundaries and grain boundaries? Or is it on a particular?
Actually, I thought it was the next slide. That's the following slide. So I'll get to that. Right? I'll get to that. So just for completeness, and I won't go much further into this, so you can imagine you have two different types of boundaries, a tilt boundary, right, shown here, tilt angle. You can generate this by edge dislocations. That's what I've been showing in these other cartoons. Or you can take screw dislocations, but then it gets quickly very complicated. You need different sets of screw dislocations to produce a twist boundary. And I'll show anyway that for silicates in general, the idea that you generate grain boundaries by dislocations doesn't really apply. Right? This is a basic concept that applies in metals, but for silicates with more complicated crystal structures, you have, as you saw, interior dislocations, but the grain boundaries are different. Coming back to the grain boundary energy or classification of grain boundaries, so again, going quite a ways back, the Reed-Shockley equation, you can calculate the energy of the grain boundary, right? So the grain boundary has extra energy relative to the grain interior, and you can calculate that, and it's relatively straightforward. As you'll see, the Burgers vector comes in here again, so everything is referred back to the crystallographic structure. That's really the key point here, that the crystal structure determines all of these properties. So I'm not going into the details, so the shear modulus in here as well. Closer to the question, what is a subgrain boundary versus grain boundary? If you calculate this, so here's the normalized grain boundary energy, so just normalized by the maximum. And you can see that grain boundary energy increases very quickly with increasing misorientation, right? So, the first few degrees, you have the steepest increase, and then it sort of levels off. And this essentially is then the classification of grain boundaries. So subgrain boundaries, these are very small misorientations. And you saw that for olivine, there's actually a real big difference in that you can image subgrain boundaries consisting of dislocations, right? And they have very low misorientation angles. So the rotation that you impart by these subgrain boundaries is only a few degrees, right? Down here, just a few degrees, and these cutoff values here are pretty much arbitrary. Well, not entirely arbitrary, but it's convention, or it's becoming convention more or less with the advent of EBSD. You need to somehow define grain boundaries, and then typically you say that 10 degrees, that's a grain boundary. Everything less than that is a low angle or subgrain boundary, and everything more than that is a high angle grain boundary. But you can see here, right, it's a continuous curve. You could have well picked 11 degrees. There's not really any difference. The key part is, small angles and then subgrain boundaries for olivine do have a particular meaning in that they consist of dislocations. Right? So, but otherwise, that's a convention. Yeah, again, going to something with a much more simple crystal structure, nickel oxide. You have a rotation axis, and you rotate, bicrystal around this axis. And you actually find these minima corresponding to distinct crystallographic orientations. That's, again, a concept that comes from these simple crystalline structures that don't apply to the more complicated silicates. In effect, what you're saying is that, you saw the cesium chloride structure. If you rotate that, you have certain orientations where the atoms on two sides match. You form a superlattice, essentially, of matching sides across the boundary. If with the more complicated crystal structures of silicates, you can't really do that. Right? They're too complicated. You can't define a superlattice. So basically, the important part is here you measure grain boundary energy versus surface energy, so a free surface. And you can see that for the first few degrees here, the grain boundary energy increases steeply. That's really the important point, right? The grain boundary energy increases steeply, and you can visualize that actually very nicely. The surface energies, yeah?
How are you measuring or estimating the grain
In this particular study, I don't know, but for example, here is one way of doing that. So what you have here is olivine, right? So these are essentially, well, 2 olivine crystals with a subgrain boundary, right? So subgrain boundary, small misorientation, less than 5 degrees, or less than 3 degrees in this case. You can see again here, these are arrays of dislocations, right? The subgrain boundary is formed by arrays of dislocations. Here you have a high angle grain boundary. Right? And you can check that with the TM, you can get a diffraction pattern, you can get the orientations of these grains. So high angle grain boundary, meaning the misorientation is tens of degrees. So if you then put a little bit of melt in the system, you can see, so here in this pocket here, we have melt, well, quenched to glass at high temperatures. This is a melt, a basaltic melt. And you can see the geometry is different. Here we have a very large, what's called a dihedral angle. And the concept is outlined here, right? The angle between 2 solid grains in the melt, that's the dihedral angle. And then you can see that this angle here at the subgrain boundary is much larger than the angle here at the grain boundary, at the high angle grain boundary, right? Meaning that this energy here, the grain boundary energy along this subgrain wall, is much smaller than the energy along the high angle grain boundary. Right? And you can calculate that, the formula, so basically it's force balance. You can imagine vectors here. These are surface tensions. And you can calculate a force balance out of these vectors. And you have the solid-solid surface energy, the solid-liquid energy, of course. You have to take into account here the surface energy of the solid with the liquid. And if you look at this, it turns out that, measuring grain boundary energies, so here the surface energy is the grain boundary energy is much lower than the grain boundary energy here. Yeah, Matt.
What are these interesting looking structures in the subgrain boundary?
Here?
An echelon.
These are dislocations, right? So the subgrain boundary is formed from dislocation. So if you go back, I can show you afterwards that the slide where I showed that nice mesh, so this, we're just looking at more edge on such a mesh, right? So if you tilted in the TM this crystal, you'd see again some sort of mesh of dislocations. So this is a subgrain boundary that's formed by individual dislocations. And that's really key, right? This is one of the big differences between a subgrain boundary and a grain boundary. That's what I said in the olivine, and I'll show more pictures. You don't see any evidence for dislocation structures on the grain boundary. These only time you see these are these subgrain boundaries. Yep?
I'm more accustomed to seeing these dihedral angles in solid liquid cases where the fluids are free,
so you mean a drop on a solid surface? So you can take, say, cut a crystal in half and put a drop on the surface. Is that what you're talking about?
Sure, but then you have air.
Right. You have an air, liquid, solid. Right. So the surface tensions here balance along the interfaces. I'm not entirely sure. So so ultimately, I don't know whether I get to that. If you look at grain growth, so you have to look at surface energy, surface tension balance here for the system as a whole, right? But to first order, the geometry of the glass here is determined by the surface tension, by the surface energy. Yeah?
Two questions. First, is there a thin film melt all the way along that high angle grain?
So I'll get to this a little bit, and the answer is no. Essentially, you can, as another thing, you can see here very nicely, right? So the grain boundary here is almost parallel to the electron beam, right? It's a three-dimensional problem. You have a thin foil. The electron beam is going through these two olivine grains. And here, at least, right, the thickness of the grain boundary is at a minimum. You can see on this side, right, you probably, you have a change of orientation of the crystal. So on this side, the grain boundary isn't exactly parallel anymore to the electron beam. So that's essentially an artifact, and that's an important point. I'll get to that in one of the next images, that you have to take into account the orientation of the grain boundary, right? It's a three-dimensional object, right? It can have a slope in the third dimension.
Ian Rose's question, I think, was in this geometry here, you've got three solid grains nominally. I guess one's a subgrain boundary, and then a liquid. And if you think about a solid as something that's not deforming, why does the surface tension matter? So he said, well, if you have a liquid, gas, solid interface, the position of that interface can adjust to accommodate that energy balance. But here the grains are fixed, and you said you introduced a liquid, and why wouldn't the liquid just fill whatever geometry you gave it?
Because you do, it's not quite as simple, right? You can dissolve things at the surface, right? So that's no. So it gets a little bit more complicated. In a static system, this is an equilibrium situation, right? So essentially, you are able to dissolve, a piece of the olivine, like atoms or building blocks of the olivine, silica tetrahedra, right? This is a basalt. So everything that's in the olivine is soluble in the basalt. So you can dissolve it if you have an unfavorable geometry. You dissolve it. You have if you introduce, the standard thing is if you have a sharp tip here, for example, a sharp crystalline tip, that tip will have a very high chemical potential, right? That's surrounded by two surfaces. So that high chemical potential means it's more soluble in the basalt, and so it will dissolve and then redeposit somewhere else where there's a lower chemical potential. So these are not glass balls, with water in between them. The solid is soluble in the melt, and therefore is able to adjust its surface configuration. Right? Is that better? Is that the question?
This requires it to be in some sort of equilibrium.
Yes, of course, yeah. Right. So we're assuming chemical equilibrium and then surface tension equilibrium, locally at least.
When you're talking about grain boundary energy, do you mean how easy it is to move along the boundary or some other physical properties?
No, the definition of grain boundary energy, so a lot of this comes from soap bubbles, basically, right? So if you take a soap bubble, right, it is filled with air, and the air inside the bubble is at a higher pressure than the air outside of the bubble, right? That's why you can burst the bubble. And what holds the whole thing together is that surface energy of the soap film.
So
right? And that's the same concept. So if you have an exposed surface here of the crystal, it has a certain energy, right? It basically, for a crystal, it's the broken bonds, right? You have bonds at the surface that are not satisfied, and that's an extra energy term.
So how does the grain boundary energy relate to viscosity?
We'll get to that.
Okay.
Right? So we'll get to that. That's behind a lot what comes next today or Friday. Yep, that's a good question. Right. All right. So it is a beautiful image because it shows a lot about the system, the interaction of a melt, a third phase here, but also the differences between grain boundaries and subgrain boundaries. So,
one more question.
Yes.
This all started with a question. Somebody asked a question about how do you measure grain boundary energy, and what you've shown us is a ratio of energies, but.
Right. So it's a little tricky. In the end, you have to do multiple measurements, right? One of the examples is you can do this sessile drop experiment where you can put a drop of basalt on a surface of olivine and then like a drop of water on, a piece of paper or something, or a piece of paper is not so good, but, on an oily surface, for example, you form a certain geometry, you can measure that angle. And so you have to do a number of these measurements and then backtrack what these, eventually work out what these energies are. Right? So it's a little bit roundabout, but you can measure, relative energies like that. And typically, so grain boundary energies have been measured in that way for olivine. It turns out, I won't get into that much detail, but it turns out somebody asked the question whether this is a static or dynamic system. It turns out that surface energy also drives grain growth. Right? So there is not just a local surface energy equilibrium to consider, but there's also a grain size distribution to consider, where large grains grow, small grains shrink, and it's again minimization of surface energy. So that aggregate behavior as a whole interacts with the local surface energies. So measuring grain boundary energies in great detail is not that useful because in the end, it's an evolving system. All right, so one other key point here is if you look at, so thinking about grain boundaries, And this is important because it's attractive to measure grain boundaries that you can characterize well that have small misorientation angles. But in a polycrystal, so this is for an orthorhombic system, yeah, that angle depends on the crystal symmetry, but basically the distribution of misorientation angles is peaked, somewhere here near 90 degrees or so, right? So the meaning is that the vast majority of grain boundaries in a rock are high-angle general grain boundaries. There's nothing special about them, right? This is the distribution, the random distribution. That's a measured one here. You can see it's not perfect, and the reason is we just don't have enough measurements, basically, to approximate this complete random distribution, right? So general grain boundaries have high misorientation angles. This becomes important if you look at grain boundaries, right? With a TM, it's very difficult to do large numbers of measurements. So this is again, a TEM image, polycrystalline aggregate. You can see very fine grain, so the grain size here is about 2 micron or so. You can see very nicely, these are beautiful grains, a foam texture in terms of material science, beautiful structure. This is actually phosphoride 90 olivine, so this is iron-bearing olivine that's synthetically made. And you can see that the only other imperfections that you can image at this scale here are dislocations. So we have the defects that we have in here are grain boundaries everywhere, and dislocations. So some of the questions, yep?
I was just wondering what the bright spots were.
These are pores. These are pores. So not going into too many details, but basically this is a hot pressed sample. So it was, so we make these, I won't go into detail how we make this olivine, but basically we take the olivine, which is much more fine grained, and then compress it at 12 or 1300 degrees C at 300 megapascal. And because these are melt-free, they don't sinter very well. So we would have to go to vacuum sintering to get rid of. So we retain these little gas bubbles, basically. Right? So these are pores. We argue, in the end, if you measure physical properties on these, that, for one, the aggregate is near theoretical density, so there is not a whole lot in there in these pores. And the other part is that we don't have any sensitivity of anything that we measure to these pores. And one difference is that these pores, so I'll jump ahead a little bit. So if you take a melt would be at every triple junction, so you would have a melt. These pores are clearly not at every triple junction. They're just sort of randomly. Some of them are in grain interiors, some are at triple junctions. But they're just sort of a blemish, and we're working getting rid of that, but they're not consequential, essentially. Yep?
Another quick question. So on the last slide, so the discoloration within each grain, are those subgrain boundaries, or is that compositional? So there seems to be, within a grain, so...
here, for example?
Yeah, there's some, modeling.
No, you see dislocation. So if this were a subgrain boundary, you would see that as well. That's basically, I think, just artifacts from thinning the foil. Right? These are
so
just
they might
imaging.
Be thinner, thicker.
Yeah, these are just
so
imaging.
So it's not composition.
No. Compositionally, so we know a lot about these samples. We've analyzed them all over the place. Compositionally, they're completely homogeneous. So everything that you see here, all these brightness variations, that's all imaging artifacts, basically, from foil thinning and then the imaging itself.
Why does this one grain have many more pores than...
That's just random, so the way we make these samples, we have a very fine powder. So the crystallites start out much smaller than 1 micron. And then we cold press that powder, and then we loaded the cold pressed pellets into a jacket to put it in the machine, in the Patterson rig. So that's just random distribution of pores that's left after sintering for hot pressing for 24 hours. All right, so looking at grain boundaries, so this is a high resolution, again, a TEM image, and you can see very nicely here lattice planes. These are 0, 1, 0 lattice fringes, right? So going back to the crystal structure of olivine, the 0, 1, 0 planes are the ones that are the furthest apart, right? These have the largest spacing, and therefore you can image them in the olivine structure. So this grain here at the top shows these lattice fringes very nicely, individual lattice planes. So this is where, the question of orientation. So you can see that in the TM when you put your foil in, right? The grain has an arbitrary orientation, so you have these rotational stages in the TM, you can tilt the whole sample with 2 axes, typically, in these TMs. So you rotate your crystal until you see lattice, or you rotate your foil, rather, until you see lattice planes in one side. And then the question comes, if you have a grain boundary here, you can now rotate again until your grain boundary is parallel to the beam, so that the beam goes straight parallel to the grain boundary. And most likely, or it's basically almost statistically impossible to see lattice fringes on the other side, because as you saw, right, large angle grain boundaries have these high misorientations. And in olivine, there are not very many lattice planes that have a spacing large enough that you could actually image that. Right? So it becomes very difficult to have what's called a 2-beam condition, where you actually can see lattice fringes on either side. That starts to get towards a special boundary where you have a special orientation relationship between the 2 neighboring grains. So this is important because here is when the grain boundary is parallel to the beam, right? So this is a 3-dimensional problem, right? If the beam comes vertical and the grain boundary is inclined, you can't see the true width of the grain boundary, right? The plane that you're imaging, that you're shining your electron beam through, is not the true width. You have to rotate your grain boundary such that it's parallel to the electron beam. And then you see the true width of the grain boundary, right? And so if we do this, we get that we have a grain boundary region that's about 1 nanometer wide that doesn't have this nice ordered crystal structure. Okay? So there's a grain boundary region about 1 nanometer wide, and we have a number of images, right? So different, you can see that here. You can't see any lattice fringes, but basically you have about 1 nanometer here. That was the image that I just showed. You have many different images. These are general high-angle grain boundaries, right? No special orientation relationships, nothing special about them. You just pick a polycrystalline aggregate and start the painful process of imaging grain boundaries. Right? Yeah?
These are all dangling lines, essentially.
Right. These are, you can sort of...
The width of the dangling.
So there are, ab initio calculations now. What happens, so imagine, you have unsatisfied bonds. That's your surface energy in the first place. But there's obviously something happening in here. It's not a void space. And ab initio calculations are looking at structures here of these grain boundaries. And they, become fairly complicated. But they're not ordered. Right? They're not ordered. They don't have a crystalline structure in that sense that you'd get a diffraction. Well, it would be difficult for one. Yeah, they're more ordered. So that's an important point. They're more ordered than a melt. So this was the question somewhere. Is this a melt? And basically, no, it's not a melt. It's not a bulk melt. It's more ordered than that. It's more ordered than a bulk basaltic melt, but it's not as ordered as a crystalline interior, right? So it's a third phase, and thermodynamically it's treated as such. You can calculate energies for that Gibbs free energy of a grain boundary phase, and I'll show more of that. Right? It's very important, right? That this is a separate phase, and in fact, when we do seismic property measurements, we basically characterizing the viscosity of this disordered layer that's about 1 nanometer wide. Right?
Different bulk properties too.
Right, because you can slide the 2 grains. So that'll be on Friday. You can slide the 2 grains on that layer here that's about 1 nanometer wide. You can slide them past each other because the viscosity of this layer is lower than the viscosity of the grain interior. Right? Yeah?
What happens when you start adding stuff to the olivine, like you add dirt?
Right, so I'll show that a little bit. Yeah, I'll show that actually. One more thing before I get to that. So another thing, I said olivine grain boundaries, and the other important part is you don't see any evidence of dislocations, right? You can clearly see dislocations in subgrain boundaries or grain interiors. There's no indication, none of these pressure shadows from the dislocation cores, right? It's just a smooth line. So the other thing we don't see, this is a strontium titanate perovskite that has these very nice steps, and they in fact correspond to certain crystallographic planes. And this is the only material where I could find a picture from our lab. So this particular perovskite, it's a perovskite analog, was used for measuring properties of perovskite. It has these peculiar steps on the grain boundary. Olivine does not do that. We have not seen an olivine grain boundary. So we looked at many grain boundaries. We've not seen olivine do that. So olivine does not have, so here, no steps, no dislocations. this material, for some reason, does that. But for example, calcium titanate perovskite does not. So it's how this came about, but clearly crystallographically controlled in this case. So grain boundary analysis by TEM. This is, so you have a disordered region, so it's fair to ask what's the composition of that. And we've done that. So EDS spectroscopy, basically you have to form an elongate beam along the grain boundary and compare that to grain analysis from the grain interior. And if you do that, and these are not very quantitative analysis, so we're just looking at peak, so in the EDS spectrum, the peak due to a certain element relative to the background. And what essentially this shows here, so we have calcium, aluminium, titanium, so this is the dirt. These are the trace elements that are found in the interior of olivine. And you can see that the interiors, so everything that's green in these three different samples here, everything that's green as a green symbol, that's a grain interior analysis. We know that olivine, natural olivine, has calcium, aluminium, titanium as a trace element in it. So the grain interiors will have a little bit, but you can clearly see from the red symbols here, right? These are grain boundary analysis. So the difference here, grain interior, grain boundary analysis. So the red symbols, you can see that all of these elements are essentially enriched in the grain boundary region. So there's more calcium, there's more aluminium, there's more titanium in the grain boundary than in the grain interior. Yep?
If you have even more incompatible elements, can you eventually get really enriched grain boundaries and trace, in really compatible trace elements?
Yeah, it's an interesting idea, and people have looked at that a little bit. There are two things. One is that ab initio calculations do start to show that there is some ordering to it. So you can't just put anything in any quantity in the grain boundary. It's also only in 1 nanometer wide region. So there is some limit to that.
Say you have garnet or something to accommodate
Ha. Yeah, so we don't really know, I don't know much about garnet grain boundaries, other than you can go to certain types of garnets that are used for lasers. They probably know more about grain boundaries, but they're probably very pure too. Yes, the other part though is people have done that exercise, right? You can calculate the volume of a 1 nanometer wide layer depending on grain size and do the budgeting, and it turns out that at least in one such paper that I'm aware of, your volume on the grain boundary is just too small to hold even trace elements, right? So it turns out that most of the trace elements are still in grain interiors rather than in grain boundaries. So, but that's an interesting idea, certainly. So the key part is the grain boundary regions enriched, and this is still discussion here, right? This is a paper from Hiraga and others. They find again an enrichment in this grain boundary region here, distance in nanometers. So aluminium, calcium. They have nickel, titanium. So that's enriched. But what they're doing here, this is the two-beam condition that I described. So they actually see lattice fringes on both sides. But the question then is this grain boundary really parallel to the electron beam, right? So they seem to show abutting crystal planes, but it's not clear. So it's virtually impossible to get lattice planes on either side and the grain boundary parallel to the electron beam. And in particular, if you go into this polycrystalline aggregate, right, you have many grain boundaries. So basically, when we image these, we find always this 1 nanometer wide region. But that's a discussion that's somewhat ongoing in the literature. Right? That's by far not settled.
So they would claim that the grain boundary region is broader.
No, they would claim, wow, this is where it gets difficult, right? They would say that there is no grain boundary region. The crystal lattice planes directly abut.
But then they see this distributed over 10.
Right, and certainly that's a resolution question, right? So it's the same. You can't resolve at 1 nanometer. Your electron beam is bigger than that, so you don't know how wide this distribution actually is. It could be 1 nanometers, right? You can't resolve that yet in the TM. So that's a little bit the contradiction. That's partly why we're arguing that this is not a general. This is not how an olivine grain boundary looks like. Plus. But you have to put these somewhere, right? So the concentration here is much higher than in the grain interior, right? So in the grain interior, you have much lower concentrations. So they Exactly, right? So you have some region at the grain boundary that is enriched relative to what you can put in the interior. And it turns out we've done experiments on that a little bit. So the grain boundary composition correlates with the grain interior composition. So if you have an olivine that has very little calcium in it, the grain boundary also has little calcium. If you add calcium to the olivine, the grain boundary region has more calcium. So it's a phase in the sense that it has a partitioning, right? So in that sense, that's a little bit, a contradiction that you have this enrichment, but then you're saying that, you have lattice planes that are butt. So getting started on flow laws. So you can derive these flow laws from first principles. There is a physical model for all these flow laws, but in the end, what you're aiming for is what Michael mentioned yesterday: these constitutive equations relating strain rate and stress. I won't go through the derivation. I'll just try to highlight some of the important points. So one place where this is done, the full derivation here is in Poirier, for example, creep of crystals, but that goes back to the metallurgy. Most of these models come from the 60s or so. So rather than concentrate on the details of a particular model, because it turns out there are many different kinds, particularly when you come to dislocations, I'll just highlight what I think are the important points. So for diffusion creep then, so you have a pure shear deformation of a crystal, what's called Nabarro-Herring creep, right? The guys who derived these equations, derived these models basically. The idea is that you have not a pressure but a deviatoric stress. So you have a difference in stress between here and here, right? So that difference in stress, so now thinking back, I started out talking about point defects. That stress, a pressure basically on the sides of the crystal, modifies the concentration of the point defects, right? Going all the way back to the beginning when I started talking about thermodynamics, you can see that the concentration of point defects is affected by the environment, by the stress on a surface of a crystal. And that stress, so here compression, here tension, that sets up gradients in defects. And chemically, once you have a gradient in a defect, you tend to diffuse down the gradient. And of course, you can have atoms and you can have vacancies, right? You can have interstitials or you can have holes. And these then would diffuse in opposite directions. So the compressive stress, that's sort of intuitive on this phase here, reduces the number of vacancies, right? You're pushing on it, so a vacancy carries an extra energy penalty, basically. And so when there is tension here, you diffuse the vacancies from compression to tension, right? And then, of course, charge balancing, everything else, the atoms diffuse in the opposite direction. So overall, that sets up a diffusive flux. So the sequence is essentially differential stress, sets up concentration gradients, that leads to diffusion, right? So the physical principles behind this is pretty straightforward. Differential stress, a chemical potential, a concentration gradient. And then the important ingredients in the derivation of these constitutive equations are that concentration gradient, you're diffusing over the scale of the grain. So here enters the grain size. That's the important part, right? Because your diffusion goes from one phase to the other phase. That's the grain size. And so in this diffusion creep model, you enter the grain size. And then the other part, of course, diffusion creep is diffusivity. So this depends on the atomic species, right? It depends in the olivine, for example. You can see, if you think about the crystal structure, right? The oxygen will diffuse differently than the magnesium will diffuse differently than the silicon, right? These atomic species that make up the olivine, they'll have different diffusivities. And it also then, of course, depends on the crystal structure. So the olivine in particular, right, you can see that diffusion could be anisotropic because you have the arrangement of the unit cell. You have closer spaced or atoms are further apart. So anisotropic diffusion, but also like a pyroxene will have a different diffusivity than an olivine because the bonding environment of each species is different. So diffusivity is important. And then also temperature, right? Temperature determines the point defect concentration in the first place. So the long story here, so you then get a flow law, a constitutive equation. So the strain rate, the change in length or size of that crystal, so epsilon dot, so d epsilon dt, that's the equation, or another equation here. A constant, here the stress, right? It depends how much stress you apply. Here we have the grain size, right? That comes out of this concentration gradient over a grain. And then here, this essentially comes out of the diffusivity, right? The diffusivity, they're exponentially dependent on temperature, right? So in a standard, if you do a diffusion experiments, and again, that's related to defect concentration and mobility, right? You have a temperature dependent, but for the Earth, again, equally as important, not just an activation energy for temperature, but also an activation volume for pressure, right? It goes all the way back to these, potentials in the crystal lattice, the enthalpy that's here, that's part of what is behind the diffusivity of each of these atomic species, right? So at the bottom here is a different equation, again, the epsilon dt, now a constant. So here, these parameters, basically, if you do it from first principles, right, in here you have the self-diffusion coefficient that has the temperature dependent in it, the molecular volume, atomic volume, and so on. So this is the equation, how it looks like when you do the first principles derivation. So and this is where it gets a little bit interesting as an experimentalist. Essentially, for example, molar atomic volumes, if you try to, so there's two different approaches, I guess. You can take a separate diffusivity measurement and plug those numbers in, and then you can a separate measurement of this and plug that in, and then you have this constant here left. Or you just lump these parameters here into one parameter, because all of these will have uncertainties in the end, and you just fit your experimental data to an expression like this. So you have experimental data, you have a strain rate that you measure, you have a stress that you apply that you can measure, and then you measure, so stress and strain rate are measured, you measure your grain size, and then you determine your activation energy and your activation volume, right? So instead of trying to work with this more complicated formula, basically use this empirical formula. The other part of this is then, it turns out, of course, if you do these experiments here from diffusion creep, the prediction is that the strain rate is linearly dependent on stress, right? In your model, if you go back to the model here, you get a linear stress dependence. If you do the measurement, it turns out that the stress dependence is not always perfectly linear, right? And so, that's where you have to transition a little bit from these first principles equations here to something that you measure in the experiments, and you basically have to fit in as an experimental parameter. Yep.
So the term that's e to the minus e plus pv over rt, that term in the bottom would be contained in the self-diffusion.
That's where, so this dsd is a d naught times the exponential, okay, basically.
So then the a up there is not the same as the a
no.
down there.
No, the a is just a constant, and that a here has eaten up a whole bunch of other constants, like the d naught from this parameter, like the volume here. So that's all lumped, but basically you don't measure that separately. You just have a free parameter that you fit in your experiments.
So this free parameter, so the value of this the constant that you get, the a, how well are they able to predict the values that you measure based on ab initio calculation?
That has, so this is the point, this has nothing to do anymore with any kind of ab initio calculation.
But I thought you said it's a conglomeration of those guys.
Yeah, but it turns out that, this is where, so the next thing is, okay, I should probably stop at some point, but the next thing is, right, so we're talking about diffusion here, so the activation energy should be that of diffusion. But it turns out that the activation energy is an activation energy you measure. It's not directly related to, it's not equatable to a diffusion activation energy. So the point is the process is clearly more complicated. You don't just have simple diffusion of one species. It's probably a combination of processes, and one of them is dominant, but there's others that are contributing. I'll talk a little bit more about that next time. But yeah, so this is where I'm just cautioning that yes, you can do that, but what you measure then does not necessarily correspond to the perfect model. Yeah.
Is it correct to assume that this diffusion process is appropriate for point defects but not for dislocations?
So I'll do that on Friday, right? So yes, but yeah. So I'll go over dislocation creep on Friday. Yeah.
I have a question. In terms of the model that you showed at the beginning, where you had several species and you had to move several around to conserve charge, how does that come back into this, where you have many things that are hopping around?
So that's the next slide, right? So I just have to stop at some point. But so diffusion creep. So the slowest species along its fastest path is rate controlling, right? So for olivine, you have silicon, magnesium, and oxygen. Oxygen is here. So the grain interior diffusivities. So silicon is the slowest to diffuse, right? You can look at the bonding environment. The silicon is in that silica tetrahedron that's tightly bonded to the oxygen, so it's very difficult to diffuse silicon. Magnesium, on the other hand, can much more easily diffuse through the crystal structure. So, but the rate limiting part is if you want to deform, you have to diffuse the silicon as well. So the slowest species is the rate controlling one. But then the fastest path, this is where the grain boundaries come in. I might as well finish that. So grain boundary diffusivity here of silicon is faster than grain interior diffusivity. So instead of diffusing through the interior like in my cartoon, the silicon diffuses along the grain boundary. We're going back to this all-important grain boundary region, right? That's less ordered than the interior, therefore has faster diffusivities, right? These are measured grain boundary diffusivities. So diffusion, the slowest species along the fastest path along the grain boundary, and then the important part is that the grain size exponent changes. So that's something you can measure in the lab, this grain size exponent. For a grain interior diffusion, we have a squared grain size dependence. For grain boundary diffusion, we have a cubic grain size dependence. And in that far, that's what we measure actually in the lab. Yep?
Do you need to worry about generating new vacancies for this? It seems like you're probably setting up concentration gradient.
So an extra source, the model typically assumes that the concentration of vacancies is controlled by temperature. Right? So no. Yeah. No, you're not going to run out in that model. Yeah. So I'll continue this on Friday. There's a few more things. So, okay.
Before we kind of adjourn for lunch, so we reconvene at 2 o'clock for Rich's tutorial, and then there'll be a coffee break. And depending on how you do on the tutorial, you may want to continue a little bit after the break or not. But I suggested that we reconvene at 4:30 to hear the last part of Alan's talk, and then Max's talk. Okay.